Hi, good morning. My name is Hancock. I'm from Supermicro. And today I will have my co-speaker. His name is Chou. He's our software architect for the open source solution. So today we will have some update to share with you the OSF that we have working on the Supermicro's platform. It will mainly focus on what we have done and what we are going to do. So here's our agenda to cover for today. And as you may already saw some information from the OCP OSF wiki site, for the several user cases, there are already 2 existing examples of the OSF could be seen for today. So the first topic that we are going to cover is about the experience and the status of the coreboot and plus the Linux boot that we have done on our product. And to be as the first example to share with you. And the second topic will focus on the using OpenEDK tool that we have experienced and what the status we have on the Supermicro product. That will be the second example to share with you. So the last topic, we will talk about a little bit the next steps that Supermicro is going to do about the OSF development. We may seek for the possibility to have the collaboration with anyone may be interested in OSF development for future. So now I'm handing over the the first topic to Simon.
Hi, hello everyone. So just like previous session, I think Johnny already have a detailed introduction about those components in the coreboot. And here we like to highlight from the high level point of view, we also took the Intel FSP binary plus coreboot, and also those motherboard configuration for our board design plus Linux boot, and we can successfully boot up our main board within 1 minute. As you can see, let's move on to desktop. Yeah, and we also believe that with continuous enhancement in the coreboot and the various components, I think the boot time can be further reduced. And this slide, we are going to share that for our 2 platforms. One is dual circuit. It's also for software rapid, and another one is a single circuit. But actually, the thing need to be done when you got the coreboot repository, you got the source code. The thing need to be done are quite similar. Yeah. So the first thing is that you need to check on your board design which flash size was used. Because if you have an Intel Ultra CD, you know the 64 megabyte flash size is used. But in our platform, we are using a 32. So the first thing, we duplicate the project folder from coreboot from the Ultra CD folder, and we made the change according to our flash layout. Of course, you need to look into the detail, like various components on the flash, and try to string the size. Yeah. And the next thing, we start looking into what's the hardware difference between Intel Ultra CD and our platform, right? So we try to configure like a CPU socket, like the memory module, and also PCIe bifurcation, GPIO setting, etc. Yeah. So once all those basic modifications are done, next thing we need to check whether the memory training can be complete. Yeah, so in our case, that's our DDR5 the module, so we need to make sure that it can be finished. Also, the training result can be saved to the flash region. That's a dedicated region used by coreboot. It's called MRC. And with such a result, and next boot time can be much shorter because we just reuse the training figure from last time. Yeah. Okay. One last item, let's say, I think for the boot screen, we used a different approach. Yeah, I think most of experienced BIOS engineer, they will use option row. But we look into coreboot, we realize there's SP driver as well. So we try to do some mini modification. We are able to bring the BGA controller into the frame buffer mode. So that's for high resolution display. And we also made some change in coreboot. So when we change the kernel configuration, we don't use the VGA test mode. We change to use the frame buffer mode, so it's much easier for you to change your screen resolution. Yeah. Okay, we would like also to highlight, so besides those hardware related to change, I think the first thing for the firmware engineer is like you need to make sure you can get the BIOS debug message right. You want to get a message from the coreboot, like, so you can verify all those changes you made can be done in the debug message. Yeah. And second thing is like as we initialize the VGA controller, so we start to look into whether like as we expected. So we look into the kernel early print information. We also look into the system log, like output from Ubuntu GNU Display Manager. It's for kind of troubleshooting. You try to combine various debugger logs to find what's the problem. Yeah. And regarding the boot time optimization, once you have the basic initialization, you want to make the boot time shorter. So we would suggest you take the release build of Intel EcoStream FSP from the coreboot repository directory, because that will really save you your time. Yeah. If you use a debug version, that's around maybe 3 to 5 minutes, but with the release version, that's much shorter. Yeah. And if you want to make some further enhancement, you probably you need to look into what's the local level used in coreboot and also in Linux boot. Yeah, because it's up to your product phase, right? If you almost finish all the development, you want to reduce the debug level, so that will also save your time on the boot time. Yeah. So for remaining time, I will hand over to Hancock to have more, to share more experience on EDK2.
Okay, thank you, Simon. And let's move to the second topic about using EDK2. Oh, sorry.
My bad. Yeah, okay. Just one more slide. For all the OSF member, we started contributing to a white paper, which is a document. We are trying to provide more guidance for those new OSF coreboot user. And for Supermicro, we are contributing to those topics like how you can get a source code from coreboot repository. It's dedicated for software repeat. And the asset control actually reuse your ID on GitHub, but we also provide those guidance how you can combine these two things and be able to get the source code from the coreboot repository. And based on Ultra City CRB, we also provide the instruction how you set up a build environment, which package you need to install, and you type the command to build the OS image for Intel Ultra City CRB. And so one is like, then you want to deploy your image onto the flash, right? So there are several choices. We also offer the guidance, how to use a tool to program the BIOS flash with the OSF image, okay? And this one is like, as you know, the whole booting process across different software components. So for each one, how you can customize the debug console, that's quite important. You want to troubleshooting, you want to get more information, you want to get all kinds of statistics, right? So we also provide the guidance on Intel FSP, coreboot, and also target OS, how you can do that. Yeah.
Okay, thank you, Simon. So now is really we need to move to the second topic. So we'll talk about how we use the OpenEDK2 for the OS development. So from the year of 2021, that Supermicro, we took the motherboard, which is used for the one-use system, that is the general purpose server, that is with the Intel Whitley Ice Lake platform as a target. So as you can see here, that it's a very simple architecture that you will keep seeing that. So within the boot room that we use the EDK2 for the UEFI and plus the Intel FSP for the initialization. then for sure that we will need the member setting based on our hardware design. So integrate all these key components together and do some issue fix and customization. So you will have your own open system firmware, and then the motherboard could be put up successfully to the OS. So at this point, you can think about it as a firmware owner, not like just Supermicro. It could be any one of you that you, based on the flexibility of the open source, that you can build your own open system firmware just based on what the feature you really need and integrate the key components what you really want and to come out your preference open system firmware based on your hardware. So it also help you to unblock the limitation and inconvenience due to the closed source BIOS in before. So let's see another example here. So for some other user cases and demands that some maybe want to have the Linux boot to replace the Dixie space of the UEFI for whatever reasons. So you can see the similar architecture here, but with the different key components that upon the same motherboard we took. So you can see that UEFI, we use the OpenETK2 just for the bootloader only, and integrate with the FSP for the initialization, and for sure the motherboard setting based on the hardware design. So finally, integrate with the Linux boot together to come out the new open system firmware with another architecture. So again, the flexibility of the open source gives you the chance to, based on what you really need, to come out your system firmware. Okay, so let's see the experimental features that we have done on Supermicro's motherboards. So the first one that we enable the KCS host interface for the basic communication with BMC. And also, we provided the indication of the BMC IP address during the post stage. And for sure that we must enable the overall BMC network setting for the BIOS setup menu. And then we continually to optimize the overall boot time with the appropriate feature setting and the configuration setting. So, and for the new host interface that we're working on the Ravish and also investigating for some other possibility will be decided by the industrial standard. So, and then for some traditional requirement that some customers still want to see the early display during the post. So we enable the logo screen during the post stage with using the PNG, which is the format will be with the less file size, but the resolution is good enough for that kind of a traditional requirement. And like we have mentioned several times that the other features such as the RAS and the other communication with the other firmware that we're working on that. So like we have talked about earlier, that the flexibility of the open source, it gives you the it gives you the possibility to make your own decision to come out the feature you really need. So here we can look at the boot time comparison that we have done for the closed source we have before. And also we have measured the EDK2 and the EDK2 plus the Linux boot. So you can see that no matter use the purely EDK2 or EDK2 plus the Linux boot, the overall boot time will be better than the closed source BIOS. And the most key important things is with the open source, with the open system firmware that just like we talked, you can have the chance to keep optimize the overall boot time with the feature that you need or you don't need, and to get the real optimized boot time to fit your expectation. And that will help you to unblock the limitation due to the previous closed source BIOS. It's very difficult to do the optimization for that. So this slide shows you another kind of the comparison As you can see that we have done several platforms, includes the Intel Whitley with the Ice Lake platform, and also the Eagle String with the Sapphire Rapids CPU for both dual socket and single socket. So upon the Intel FSP support readiness, that you can see no matter the dispatch mode or the API mode support from the Intel FSP with the different bootloader, the overall boot time, you can see it will be in average less than 1 minute, and either can put to the Linux or Windows. So again, it provides you the flexibility to make your own decision to come out your system firmware. So let's move to the last topic. So this is about the next step Supermicro is going to do with the open system firmware. So for sure that based on the leading product we already have with the open system firmware, we will keep enabling for more the platform with the open system firmware. And also we'll keep working on the features such as the RAS, especially for the different bootloader, we have a different mechanism and framework that we need to be done for those different bootloader. And continuously to keep improve our performance to enhance the boot time. And also the communication mechanism with OpenBMC, that will be another key points between the OpenBMC and the open system firmware. So we are asking for everybody to get involved into the OCP OSF project to collaborate with us and the other project members. And if you have any comments or any idea you would like to share with us, so please go to our demo that we have our demo at the OCP Experience Center. And we are looking for the collaboration with all of you. So thank you for today.
Thank you.